Hello, Yak.
Hello, Dr. Chen. How are you doing?
Very good. So this is actually our last lecture. Hey, Kevin.
Hey,
Hello, how are you?
Hello.
doing good.
Good, good. You guys can hear me. That's good. So, welcome, and we are going to have our last lecture. So this is week 15a. So we are going to cancel B, so you have more time to prepare your FISP. Okay. So we are going to have, this is actually 27, okay, 27. So we are going to have our last lecture today. So focus independent study and presentation. Are you guys working on it? Yes. So last time we basically covered finite time LQR examples. Um, and then we talked about infinite time LQR problem. And then we talked about the ARE. So we're from RDE to ARE, okay? Riccati differential equation to algebraic Riccati equation. Okay. All right. So I hope we know that the optimal control, when we talk about optimal control, we're talking about optimal control signal in terms of U of T star. But interestingly, we end up with minus k t x t is a control law. So that's a beautiful side of that LQR problem. Today we are going to talk about LQG, so linear quadratic Gaussian. Most of the slides are from Princeton, Professor Stengel's course material. And we also have LQG design, a dedicated website for MATLAB commands, okay? In here, we are going to learn a Kalman filter, okay? Kalman filter. So you probably heard about Kalman filtering, but probably it's not that systematic. So today I'm going to tell you exactly how Kalman filter is derived and talking in the linear time invariant system. So, and there are some beautiful results in the LQG side. So, okay. So this is the outline for today. So again, we talk about linear dynamic system, multivariable. Okay, of course, it's a minor, but it's linear time invariant. We're going to talk two important issues about certainty, equivalence, and the separation theorem. Basically, we already touched a little bit. So basically, we talked about when you have observer-based control. Okay, so you have an estimator, then you treat the x hat as if it's the real x, then you design your state feedback, okay? So the u is minus k x hat, okay? So the state feedback, okay, control and the observer-based control, okay, is actually a separation, meaning estimation and control, they are separated. Then we're going to talk about asymptotic stability and for the constant gain LQG regulator, okay? We talked about a regulator, okay? Regulator. So that means the reference is zero or constant, okay? Okay. So that's the major part. Then these are the topics are more advanced. So we probably will end up here, okay? These are the modern topics, mainly by Professor Stengel's group. Stengel's group. They basically focus on stochastic robustness versus neighboring optimal stochastic control. We're not going to talk about these two. There's figure in here. You can see. Do you see this is very similar? Yes, it is very similar. So one of them is LQ design. Okay, one is LQG design. You can see their performance looks very similar. Okay, so bear in mind, LQG, although it's a totally different framework, but in practice, the results are very close to LQ. In fact, there's some duality there. So let's start. Okay. So we're not very unfamiliar with this one. So we have a LTI system, but remember we don't use ABCD here. So this is a continuous time. So this is a continuous time. Of course, we haven't talked about discrete time. I believe they are very close. So these are the time constant matrices. But Z is my output, okay? But on the output, I have noise term, okay? I have a noise term, okay? And also W here also is a noise, okay? So it's called a state noise and output noise. So in a state equation and in output equation, you have also a measurement noise. So this is more realistic. Remember in a LQR, we don't have this W, this N, zero. It's a noise free. That's not very practical, okay? So what we want to do is to minimize. So you have of course, they write X transpose QX plus U transpose RU. So this is just a compact notation, okay? Compact notation. So this is the same, okay? Same. So here I have terminal cost, okay? Terminal cost. TF is my terminal cost, okay? So this is, remember, when I have a randomness in here, I have a randomness N. So what is X? X is also random, okay? Okay, X is also random. So X is random, X is random. You do multiplication is also a vector random process. So everything is random, okay? Everything is random, okay? So this is actually a conditional expectation. Conditional expectation. Giving this, we have this. Then these are our random. So then it's E is expectation, okay? It's kind of average, okay? Average. And the same idea is here. So what is a JD? JD is we already are giving, okay? giving the control U, giving estimation of my x hat, giving my um, time varying gain. Okay, so giving that, I'm going to generate the trajectory. Okay, so then we are trying to minimize with respect to the U. So with respect to the U, so minimize the U. So the whole thing is J. Okay, the whole thing is J. So that's the problem formulation. Well, the difference is one is we have noise. We should treat everything as a stochastic. It's a stochastic. It should be random. Okay. But I want to give you a warning here. I have a warning. Okay. Because everything is stochastic. So do a differentiation of a stochastic process is basically wrong. Okay. So writing in this way is just for traditional sense. But in reality, we should not, mathematically rigorously speaking, we should not do this. We should not write differential equation. We should write an integral equation. Okay. So basically, you should not. So dx dt does not exist because you have certain noise is not differentiable, right? So this does not exist. So a lot of people didn't realize that. Does not exist. So there's a dedicated subject area. It's like a few hundred pages long book. It's called Stochastic Differential Equation and Stochastic Control Theory. Okay, we are not going to talk that way. We just use our engineering point of view. They will pretend this is okay. Okay, pretend it's okay. Otherwise, everything is good. Okay, everything is good. So integration of a noise is okay, but differentiation is not okay. I just gave you this warning, okay? But don't worry too much on many of the textbooks simply write this way. You have a noise in here, then you still do x dot. That's okay. That's okay. But strictly mathematically speaking, this is wrong, okay? Remember that. Remember that. It's Dr. Chen who is the guy who first alerted you, okay? When you want to go to do some deeper theoretical study, this is not going to be okay. Okay, this is not going to be okay. Okay, let's move on. So this is problem formulation. So my question is, what we know about these noises? So what we know about these noises? So here we assume, okay, because everything is random. Okay, everything is random. Okay, so therefore you have to use a stats. Okay? You have to use a stats, means statistics. So you should speak about, instead of talking about initial condition, the initial condition is random. So if you talk about this mean, okay, average, okay, this is the mean or expectation. So this is my x zero hat, the mean, okay, the mean. And what is the p? Okay, the p is the variance. Okay, so this is like, so you have mean and variance. Okay, you have x0 is random, minus is the mean, and you do the transverse, so it's a variance. So this is a matrix, the variance matrix. Similarly, we assume that the noise this is state noise, this is output noise. They are zero mean, okay? They are all zero. Okay, and this is what? This is the variance, okay? Variance is also called auto covariance. okay, auto-covariance. So that is, it sometimes is also called ACF, auto-correlation function. It's basically you have W noise, you have T, okay. So this is W T plus tau, T minus tau, okay. So the distance between this one is tau, okay. So then you do an expectation of that, you'll get what? It's called R W W tau, okay? So the R W W tau is a function of this tau, okay? So usually this is R W tau is something like that. When tau is 0, it's something here. So that when tau is big, going there. So that means this process, okay? So you have T in here, you have T minus tau and T here. This is the distance of tau. How this variable and this variable, they are related. So this is called ACF, okay, or the correlation function. But this RWW0 actually is some sort of a variance, okay, some sort of variance. But in this case, this ACF is impulse function. Impulse function. In other words, this is something like this. Okay, so you know delta, right? So delta means delta 0 is not 0. Okay, and delta 0 is 0. Delta t is 0 when t is not 0. Okay. And we know that delta t dt and the integration of this one will be 1. Okay, so this is called impulse function. So when correlation function is impulse function, this W is called, white noise. Okay, white noise. The reason we call it white, we actually say this is W of t. This W of t is a random process. So then for any given t, it has nothing to do with its neighbors. So it's very, it's a zero social life. Okay. So that's a white noise. Okay. Because neighbor points has nothing to do with it. Okay. It's a self-centered only. Okay. Make sense? T has to be equal to tau to be meaningful. Okay. So the strength is not 1, so it's W. Okay, it's W. Again, these are the matrices. Could be diagonal. Okay. And N, we have the same thing. It's also white noise. And strength is, this is called strength, okay, of the white noise. If it's I, if it is I, then it's a unitary, unit white noise. So all these things, and this one is even more interesting. And if this is 0, meaning they are not correlated. Correlated is not correlated. Means the two noises are not correlated. They are independent. Okay. So with that, we check then the state and control dimension. W is my noise, and Z is R. Okay, Z is R. So we go back a slide. So n by 1. This is n by 1. What W is different. W is S. Okay, so it's different. So linear quadratic Gaussian control, we have the similar structure here. So this is like what we learned ABCD here. So you have noise times the matrix L, add into here, you got X dot. X dot is Fx and GU, so go back, Fx, GU, LW, okay? So this one, you should say X dot is Fx plus GU plus LW, okay? While here, output equation Y is, this is Y. So, but Y is coupled with the noise Z. So I'm writing a Z in here. Is my H times X plus my NT. Okay, plus my N. So remember here, I just put N directly here. That is not going to lose any generality. Okay. Okay. So we want to understand what we have here. So we have measurement. This is the signal we can get. Okay, we can get. I want this one to construct my controller, but to have a controller, then we need to estimate my my state x hat in here. But if we get the x hat in here, we do a controller gain C times x hat construct as a U. So again, you can see U is C x hat. Well, x hat is the output of an observer structure. Observer structure coming in here, you have your control signal and your Z signal in here. So everything here we are talking, any signal here we are talking is random. Is a random. Or to be precise, they are all vector stochastic processes. They are vectors, okay? So everything is just vector, okay? So how we can measure the performance? The performance is by the J. So if you have terminal cost, you have you have QR here, okay? But everything is in terms of expectation here, expectation. So when you do the expectation, okay? When you do the expectation, you are doing the expectation, giving the JD, okay? Giving the JD. But remember the JD here, okay, is linked to the P and X. All these things are all connected to the initial ones, like X0 hat, okay? Okay, so these are random as well. So everything, this is also random, okay? By evolving, it's a random. So that's why we need another expectation to count on the randomness here, okay? So that's a precise meaning. So everything in the J is a scalar. It's a deterministic scalar. It's a mean in an average sense. I know this is a little bit dazzling. We the first time have seen this. However, it is believed that LQG is a step closer to the reality because we are explicitly considering the noises, okay? The noises, right? So I hope. But otherwise, everything is similar. You have U times G, you have X, X. So this is X hat. So this is the same thing here. You have F in here, okay? F in here. So I think this is X hat in here. So it's basically like a copy of the original system, okay? Okay, well, moving. So what do we mean a separation property? That means the final control law, this guy. This is my control law, okay? And the estimation law, that is this one here. This is my estimation law, okay? This is separately derived, okay? So the derivation can be strictly independent, okay? You don't have to rely on each other, okay? So that's a separation property. There's another property called certainty equivalent, meaning what? Certainty equivalent. Although we are talking about stochastic optimal control law in here, and everything here is random, but this is not, okay? So the law itself is not, okay? The control law, so you can see that the stochastic optimal control law and the deterministic control law are the same, okay? Are the same. So the optimal estimation law, I also can be derived separately, okay? To estimate my x hat, okay? So this is saying that although we are dealing with everything stochastic, but it could be treated as deterministic, okay? Okay, could be treated, okay? Because stochastic is much demanding in the mathematic sense. But we have learned so far until this lecture, everything is deterministic, okay? Meaning we don't have a noisy, so we don't have stochastic processes. Everything is deterministic. But you should feel comfortable that now we are extending to stochastic setting, and they could be treated, okay? Treated as equivalent, okay? The same. We are going to see more soon, okay? So LQG control is certainty equivalent, in other words, okay? In other words, so although we have Gaussian noise in here, but it looks very similar to the LQR. Basically, we should say they are the same, okay? Okay, so some small differences. Let's go here, step by step. So this is my giving system states and measurements. So you have measurement noise, state noise, Z is stochastic, X is stochastic. Although I told you that X dot is strictly speaking is wrong by writing this way, but it's okay. Let's forgive that. Because at this moment, we treat the stochastic and deterministic are equivalent. Okay, so that's called certainty equivalence. Certainty equivalence. So don't feel panic. This is true. Control law is basically you have a time varying control gain in here, and if you have a giving control output, so you have some giving out command output, so you can put C of F in here. We'll come back to that later, okay? So now let's do this. It looks like very similar to the observer. So this is X hat dot. You have copy this one here, copy this one here. But now you are going to have Z, okay? It's the measured one. This is called prediction. It's also called Z hat, okay? Okay, Z hat. So so giving X hat, what is Z hat? Then what's the arrow here in the measurement? Okay, and the prediction, they have a prediction arrow. So this is called prediction arrow. Okay, so that prediction arrow you have KT here. So this is like what? This is like observer gain. Okay, this is K is my observer gain. Okay, this is C is my full state feedback gain. Okay. But remember, in the state estimation here, I don't see noises, okay? This is it's very deterministic, right? Yes. But remember, Z is stochastic. So it's still very, lots of noise in here. So we can collect terms by getting X hat. This is GC, KTH, something like that. So this is something like our previous notation for BK minus, so K is here like L times H is C, okay? H is C. So don't worry about this. So, of course, I have KZ left, but these are the terms from the control signal U. So that is all giving. So G is giving, C is giving, YC is also giving. So this is just additional given term showed up in here, okay? So what is the estimated gain? The gain is time varying, okay? And it turns out that it's then connected to P, H is my B, N minus N inverse, okay? What is N, okay? N inverse is actually the autocorrelation NT transpose T tau, okay? You do an expectation of that, you will get N delta T minus tau, okay? So this is the N, the strength, okay? So that's the inverse of that, okay? Strength of the noise, okay? Then you get you decide what is your KT. That makes sense, okay? That makes sense. And so what is the PT? PT looks familiar. So this is the Ricardo differential equation. So then this is like AP, PA transpose, okay? So you have a L is this one, the gain in W, okay? And W is my strength, okay? W is my strength. Oh, let me see W now. I suddenly record. Oh yeah, W is the strength of the noise W, okay? L is here, air transversing here. So N is my noise, okay? H is like my C, okay? So it's a P. So this is my Ricardo differential equation. And again, I'm going to have SFT in here. So SFT satisfies this. This is another Ricardo differential equation. And this is R is my control weighting matrix. Here, this is my R, okay? This is my R, okay? So this is basically my LQ, remember LQR controller, that's familiar. So G is my B, okay? Like B, G is like B, okay? Then R, so the S, this is RDE, so then Q showed up in here, Q and R. Remember Q is my state weighting matrix, the state weighting matrix. So QR like here, okay? So others are similar, similar, okay? All right. So, so in summary, okay, in summary, this is my control law. This is my time varying control gain matrix, giving like here. This is my, okay, wait. This is my observer gain matrix. So this is my observer state equation. So this is the A, like the B, the KT is in here. So this is prediction, this is prediction error, and this is this KT and CT. Again, this CT and KT actually can be computed in advance, okay? Advance. Why? Because in many cases here, like S in here, okay? S dot is something. So this is not an initial value problem, okay? It's not giving S, they are not going to give you STF, okay? This is not none, okay? Sorry, you are not giving a ST0 so that you can start to integrate this ODE, okay? Matrix ODE. It's not IV problem. So in fact, so this is, you should understand, this is a giving STF, okay? The final value, okay? Giving the final value problem. It's a final value. So then you have to go from final to the forward. So that's backward in time. So you have to integrate this matrix backward in time. Make sense? So we can definitely view the part in here as my dynamic controller with the estimator built in the feedback system. So the overall controller transfer function matrix is MIMO dynamic controller, okay? Controller, okay? But remember, in our pure AOQR problem, okay? CFS is, okay, it's a static gain matrix, okay? But however, in the observer structure, they also have this observer structure, you also have a dynamic controller, okay? Controller. So I hope I didn't confuse you. So in AOQR, with observer or without observer, so those are deterministic framework, but they don't have a cost associated with that. The maximum thing you can do is a pole placement. But the question is, you don't have a cost. How can you quantitatively tell where you put those poles? Based on what? Okay. So that's a valid question. So that's why we need AOQG. AOQG, you have explicit cost associated with that to tell whether this pole position is better than that, you know. In fact, we always say this is optimal, okay? If we have that J performance, okay? So in actually a linear quadratic regulator problem, you cannot answer the question about this. I told you in control, we need to ask two questions like how optimal and how robust. But actually there's another question, how stable. That's first thing first is number 0. Okay. we know how to answer this question, okay? Well, let's take a closer look with an example. So this is a very simple example, okay? This dynamic system is already stable without noise. These are the noises, okay? So this is like my C matrix, measurement matrix, okay? Then what is my estimator differential equation? I copied the dynamics here. And this is my observer gain. This is my observation measurements. It's true measurements, okay? And this is my estimated state times h in here. So this is a prediction. So this is prediction arrow. Using this arrow to adjust the dynamics of estimation observer dynamics, you end up with this one. Okay, that's all. If you do Laplace transform, of course, this is a size case. Okay, that's case. And in fact, I don't have a D matrix, so you have no yield, no control. Okay, so if I have no control, we don't call it observer. We call it, this is a simple estimator. Okay, estimator. So observer and estimator is probably different. Usually when we don't have the control driving, so we call estimator of states. If we have control, then we say observer. Okay. All right, estimator here. We don't have control. Did you see that? No control. So that means my G is 0 here. G is 0. Okay. So we end up in here to Laplace transform. So this is S minus this guy. You have this. So we have this. So these are the scalars. Okay. Scalars. So you have this one. X hat divided by Z, ZS. Okay. Z is my. Okay. So basically, I have a system. Okay. So I have a system. I have a measurement. Okay. And inside here, I have a internal state. Okay. So I'm going to feed this one feed this estimator, and I hope I get X hat. Okay. And I hope X hat will converge to my true X. Okay. True X. So this is called state estimator. Okay. So state estimator is basically Z is input. Okay. X hat is output. So output divided by input, equal K divided by that. So this is K is a gain, or everything is gain. So here is like A divided by S plus B. AB is all greater than 0. What's this? This is a low pass filter. Okay, low pass filter. So if you do a body plot, so this is a dB in here. So you probably have something like this. If low frequency pass and go here. The reason I'm having a shift in here, not 0 dB here, is because A divided by B may not be 1. Okay. When S is 0, DC gain here is A divided by B. Okay. Well, so you can see the theory is very complicated, but if we reduce to the first order system, then it turns out it's a simple low pass filter. Okay, simple low pass filter. So therefore, when you have the W and N with high frequency content, they will be suppressed due to this part. Okay, minus 20 dB per decade of this slope due to this one. Okay, the low pass and high suppressed is filtering. So that's why estimator is good. Okay, so let's say if I have something not stable, okay, we can do the same here, and do the same here. So we can still do that. We can still do that. Then we still end up with a low pass filter. Okay, low pass filter. Okay, so it is still possible to make this one as a stable. Okay, because you can choose the K is by your choice. You can have a stable estimator dynamics. Okay, make sense? Okay. So it's possible, although your original system is not controllable. But sorry, not stable. So steady-state scalar filter gain. So there are some questions about it. So how you choose this gain K, okay? So let's define something. Signal power is the state estimate variance, okay? The X hat variance, okay? Noise power is the variance, is the noise, okay? NT. Projection from measurement space to signal space is the H. This is the H here, H in here. W is my the variance of my omega t, WT, sorry, variance. Okay. So the constant, the gain should be PH divided by N, choosing in such a way. Then you try to solve algebraic Duality equation. So you'll see what do you get. So then you can solve the P in here. Okay, signal power. So then the P can be solved in this way. This way. Okay. So the K should be choosing. This is the P. Okay. This is the signal. Okay. Signal. P. So by some manipulation, you are going to get this equation. So in other words, in this case, if W greater than N, so that means the 1 can be ignored. So then this can be ignored, okay? So you H cancel, okay? So you end up with this one, okay? This is asymptotically. This one has meaning, okay? So that is the noise strength in here and noise strength in here. So basically your K is your observer gain, okay? Should follow your inner heart, okay? What is your heart? Heart is the ratio of the strength of the state noise and measurement noise. Although they are not related, but it turns out the K should be chosen such that it's proportional to W. It's asymptotic to W divided by N. Okay, again, let me write. You have N T N T minus tau. You have E. So this is a cycle, okay? W delta tau. So the same thing is W T W T minus tau. You have E here. You can get sorry, this should be N, okay? So W. Now you have delta tau. So if you already know that, so the K should be choosing like this ratio square root. And the unit-wise is correct because this is like variance, is the square of this, okay? With the square root from dimension point of view is a signal ratio, okay? Magnitude ratio. Okay, so let's move on. This cycle is kind of interesting. Let's talk about CE here is called certainty equivalence. The PT is independent of the UT, so my overall cost can be split in two parts. This is nothing to do with so this dynamic constraints. Okay, so identical to the form to the deterministic cost function, minimize subjective dynamic constraints based on the state estimates. So this is a state estimation function, and this looks like very deterministic, right? So we don't have noise injected in that. In the form, it looks like deterministic, okay? But I know that Z of t is a stochastic process, is random. So common Bush filter to do estimation of the state mean value, okay? How to do that? So we assume that everything is Gaussian, okay? This is important. It's Gaussian, and we treat this epsilon as my observation error, prediction error. I'm sorry, prediction error. Okay. So filter equation is analogous to deterministic dynamic constraints on deterministic cost. So as if we're talking about this one. Okay, talking about this one. Okay. So I found the control design. Okay, minimize this JCE, certainty equivalent cost. Okay, using a time varying feedback controller, using an estimated state. Okay. So the control gain is the same as the deterministic gain, like R inverse, this B, S of t. S of t is, this is a Ricard differential equation. And then, again, I already mentioned that you do not know ST0. You know this, so you have to backward integrate this RD. So backward integrate that. So two parts. First part is estimator. Sometimes it's also called common Bush filter. Actually, I met Bush in person. Oh yeah, I met common in person as well. Yeah. So this is estimator. So you copy the dynamics here, and you have a time varying gain, which is so you have a prediction error term, and they have this one. Okay, this one. So optimal cost for the continuous time LQG controller. So when you say optimal, what do you mean? Okay, so that cost, okay, is connected to the sizes of your initial state variance. Okay, this is the variance. You have square variance, and you also have the integration of S is already computed. K is also computed. N is given. So this can be obtained. And be careful here, we have a trace. Okay, I have trace. The GS term, you have mainly linked to the terminal cost, and you have another cost in here. So all these equations here can be rigorously derived. If you have the LQR, you have your LQR knowledge, it is not very hard to go through this one using a certainty equivalent argument. But if you do SDE, the stochastic differential equation side, things will be more complicated. So for discrete time, we have the similar format. So sometimes they say they use this term. So they use minus term and plus term. So what does that mean? So I have a k in here. So I introduce k minus and k plus, meaning this is a prediction, this is previous. So basically, xk plus is saying that I got my estimation, but I need to use previous. So this one is kind of recursive. They use, okay, listen, they use xk minus 1, okay, to generate xk. But this xk is not the real sk here, it's not corrected. I put this minus sign in here, do this prediction arrow, correct this, okay, correct this. Then we call it a plus, and I use that plus, put it here. And you cannot do that. This is not. You have to go here and get further corrected. Okay. So that's why in common filter you have this kind of concept. Okay. So you need to recursively update it. And many of the implementation is actually on the discrete time, and we should understand what do we mean plus, what do we mean minus. So it's exactly here. Okay. So this k minus, okay, is this one. Okay. The k plus is this one or this one. Okay. So when we say what is the estimated state, okay. So you see this is not in discrete time is not rigorous. You should distinguish about x hat k plus versus x hat k minus. Well, k minus going this way, and further correct x k minus, you get this one. I'm not sure you are confused, but this is how they deal in the discrete time. So let's take a look of first order system and common filtering estimation from a noisy measurement. So so this is a propagation of those uncertainties. You can see the uncertainty is going smaller. For the uncontrolled system, you have something like this. It's plus 1 sigma, minus 1 sigma. This estimator is red. The actual signal is blue. Blue is actual signal. Okay. And this, so blue signal is real, and this color, the first one, is measurement. Okay. Okay. So this blue one is the state, and the black, the two blacks are just plus 1 minus 1 sigma about the noise. And then this color, this is a noise disturbance. And you can see disturbance is a white noise, okay? And it is, if you check its spectrum, you are going to see that along all the omega, it's spread everywhere, okay? It's called wideband noise, wideband noise. So just give you a rough idea. If you only have a measurement, not refined, your noise is so big. But if you use a common filtering, so you are going to get a red one. Okay, the red one is common filter. Okay, so the blue one is the real signal. Original signal is a stochastic. So you can see because of x0, it is stochastic, right? random. So I want you to pay attention about error QG, error QR. So this is error QR, okay? This is error QG, okay? Don't you guys see something similar? In fact, they are, okay? They are. This is by simulation. You will see, this is the same. It's the same. Okay. So in this case, the n is 0. Okay, we don't have measurement noise. Okay, measurement noise. So we only add state noise. WT is not 0. Okay. WT is also for disturbance. So this blue one is open loop. This one, red one is a closed loop. So after closed loop, you can see the variation is smaller. Okay, so things under control. But you can see here, of course, this should be the same open loop. This is the RQG closed loop with common filtering. In this case, you can see the closed loop control is still very similar. Okay, so therefore, we can say that now this case is NT is not 0. Okay, of course, WT is not 0. So you can see this is a robust to NT, okay? The output noise. I'm kind of output noise immune, okay? So isn't this good? Of course it's good in practice. If you have measurement noise, it's not going to affect my control significantly. Isn't this good? Of course it's good, okay? So let's go through all the equations. What is the asymptotic stability of the RQG regulator? RQG linear quadratic Gaussian. So we assume we have perfect knowledge of everything of F, G, L, or none, okay? It's H and K or none. So this is called state estimation error. This is epsilon. So then the aerodynamics, okay? The aerodynamics will be affected by, this is noise, this is a noise, and this is stable. So basically it's connected to only by your observer gain, common filter gain. So if we stack them together with the original state under closed loop, so you can see if this is stable, then everything is stable, okay? So because this is upper block triangular matrix, okay? All right, so estimation error here. So will this error affect the state response? Of course it will, all right? So it's here. But on the other hand, actual state does not affect the error response. But disturbance W will affect both. So go back to this one. W will affect my error. But do we have X in here? No, I don't have X in here. No, this is state is not going to influence my error. So where is your true X? It's called true state, okay? Doesn't matter. True state doesn't matter to my observation error. No. I should not put it here. I should put it here, okay? But all this observation error and state disturbance will affect the response, not stability, okay? So, however, life is not fair and not easy, okay? And let's assume that this is observer A, B, state matrix, B matrix. You have K here. But this is your actual original system. It's not the same as F. There's some mismatching here. And also you have mismatching here. H is not the same H. Okay. So then you do the derivation. You have something similar in here. Also, you come over here, and this is not zero anymore. In other words, anything mismatching about, if you don't have a perfect knowledge about the system, or if your observer and the state, they have some mismatch, the overall closed loop control, as well as this estimated response, are all coupled, and they can affect their stability. So that's a very important message. I hope you remember. Okay. And so they also affect all the closed loop eigenvalues. That's stability, response, everything. Okay. So this coupling, due to the mismatch, okay, or uncertain parameters, can lead to instability. Okay, through improper control gain, estimator block control effect on its coupling, and the damping is redistributed or the eigenvalue modes. Okay. So there is a very famous, I put a link in here, 1978. Okay, 1978. I met John Doyle multiple times in person. Once we were in the VIP dinner and we have a very nice chatting about fractional control. But anyway, let's talk about this. So this is my noise. This is my state matrix, control distribution matrix. This is so everything is here. We do Q is scalar Q, and 1111. We just do this. That's fully populated. The W is this one. N is one. Okay, N is one. So we do controller estimator gain, and we find out the gain is connected to the Q. Depending on the Q, we can solve it. And also estimator gain K is connected to the W. Okay, we can put the W in here. So you got a CC and a KK because they are the same. Okay, you 11, you 11. Okay. So looks like it's going to work. Okay. And that paper I cut paste for you. It's only like one column. This is one column, and this is a half column. So it's 0.75 pages. So IEEE transaction automatic control. So they give this example, or they worked out the example, then they try to do closed loop transfer function. Then, so these are the, if you do have some little bit of mismatching here, or only one with mismatch, GA in here. This is G, okay? G is my B. So instead of one, I put a mu in here. Okay, put a mu in here. And then we recompute, the mu will come in here, okay? Come in here, characteristic equation. And we solve this closed loop transfer function. No, closed loop characteristic equation will be like this, okay? And we can solve what is A coefficients. And here is the Roos Hurwitz stability, and necessary condition. Mu is nominally equal to 1, but mu can force A to change sign because A1 is like this, A0 is like this. The mu, okay, if you change the mu a little bit, instead of 1, because otherwise it's 1 nominally. And let's say if we do minus mu is 1 plus epsilon, okay, very small value. So if you have arbitrarily small value, okay, will cause the instability, okay. So there's uncertainties in the control effect, so it will make things very bad. Okay, so that conclusion shocked the whole control community. Okay, so in other words, you don't have X, then you do a measurement, you have to pay price. That's all hinted about in control. Robustness issue is a must discuss issue. So this example raised a very big flag, okay? Very big flag. So in other words, we can answer another question about, can we make this mu, the nominal value is 1, remember? It's a 0, 1 in the B matrix times U. So how we can enlarge this mu, the range of the mu, okay? Okay. So the open loop is unstable, requires feedback to make it stable, guarantee the stability. So Q and W must be definite. But however, here they are not. They are positive semi-definite, both of these. Okay. So in 1979, next year, they suggest a fix. Okay. A fix. Okay. Suggest a fix. So in other words, you artificially increase the process noise, okay, the state noise, okay, or state noise by this amount, okay, by this amount to fool, okay, the estimator or the common filter, okay, common filter. So by increase this one, then you will gain better robustness, okay. So this thing is called loop transfer design. It's called loop transfer recovery, LTR. Okay, LTR. So again, you purpose the foo add this term, okay, and increase the gain K, increase the K to fool the estimator to perform, to deliver that robustness, as if you recovered from the loss of robustness, okay, so that so that your LQG will come back look like LQR, okay. All right, so I'm not going to go to details. So I want you to see more familiar slides. So you have you don't have a D, so you have a W1, W2, okay. So this is the state matrix. So then this is LQR. You don't have, everything is deterministic. And here you have W1, W2. They are with white noise with a strength V1, V2. The V1, V2 will show up on this ARE. So this is to infinity, infinity. So this is estimate this prediction error. So this is estimator, estimator. And then J is try to minimize the error here. Error is basically X minus X hat, okay? And W is my weighting matrix. Of course, W you have so you have H is solving as sigma is connected to W here. You have A sigma sigma. So this is no sorry. Sigma is my solution of this. It's like P matrix in here. So V1 sigma C V2. Okay. So you try to. This is just a weighting matrix. Okay. Sorry. So, but remember here, V2 is strictly the positive definite, okay? V2 here, okay? And so this is minimization of that. So it turns out that H, okay, H is a gain, observer gain, no observer gain, common filtering gain like this. So from left and right, you see some one-to-one relationship. Therefore, sometimes we call this as a certainty equivalent or some duality in here. Okay. So, but remember, these are the noises. We don't put any control in here. So this is just a steady evolution observation. So how to from Y, how you can construct, you can get X K hat such that the expectation is the difference between X hat and X is as small as possible. Okay, so it's a linear Gaussian system. Everything is Gaussian. So so we extend this side. Its expectation will be written as this one. The reason is omega k, epsilon k, all zero mean. Okay, zero mean. So the covariance will be this structure. So common filtering is common filtering is just to try to so you have this one is try to determine what is your k. This is observation error. H and A are known. Okay, C is known. So how to decide this k? So it turns out this k gain matrix it can be solved by this equation. And this equation is dependent on the sigma k, it's a variance. So this is a variance. This variance will be iterated through this. So then you do a recursive iteration. You will be able to get x k hat. Okay, and there's a flow chart to do this to minimize the error. Okay, so I hope you can see here LQR and common filter duality here. So this is a very clean slide. So you can see state dynamics. So after the observer, okay. So this is LQG and this is common filter. So you don't have a control, but you do something here very similar. Okay, very similar. This is a backward Riccati equation, but they are using a forward Riccati equation here. So you have to have some Gaussianity assumed. There are more advanced topics to talk beyond this duality, but otherwise everything is similar. So that's all. You can learn more about common filter. But giving LQR, LQG, then common filtering is not very hard. Okay, very hard. That's it. We have a few minutes behind. So let's take 10 minutes, and I'll be back at 6. Okay. So then we have a help session or discussion session to see whether you have any questions, problems about FISP presentation next week. And also probably a PS9 if you have any questions we can chat. Okay, I'll let you guys go and come back in 10 minutes. Bye-bye.
Bye-bye.